I'm Adam from RFOXiA, from our real lab. Today we're answering a question most builders don't think to ask until something goes wrong. Why does your platform have no reliable idea which direction it's actually facing? There are three sensors that define how a platform understands its own motion and orientation. The accelerometer measures linear acceleration, the gyroscope measures rotational rate, and the magnetometer measures the ambient magnetic field to derive absolute heading. Most builders include the first two. The third one gets skipped, misunderstood, or added as an afterthought with no calibration. And then people wonder why the drone keeps drifting northeast when it's supposed to hold position. Let me explain what each of these actually does, what it cannot do, and why the combination is not optional if you want your system to know where it is pointing. The accelerometer is the simplest of the three to reason about. It measures force. At rest, it measures gravity. That gives you tilt, pitch, and roll relative to the Earth's surface. It's stable over time. It doesn't drift, but it tells you nothing about rotation in the horizontal plane. If your drone rotates 180 degrees while level, the accelerometer registers nothing. It has no concept of north, south, or yaw. The gyroscope measures angular velocity, how fast the platform is rotating around each axis. Integrate that over time and you get angular position. Sounds clean. The problem is the word integrate. Every integration step accumulates error. The sensor has a small, continuous offset called bias, a non-zero output, even when the platform is stationary. Integrate that bias for 30 seconds and your reported heading has drifted several degrees from reality. Integrate it for 5 minutes and the number is meaningless. This is called gyroscope drift, and it is not a firmware bug. It is a physics property of the sensor. There is no amount of filtering that eliminates it without an external absolute reference. That external absolute reference is the magnetometer. The magnetometer measures the Earth's magnetic field vector. From that vector you can extract absolute magnetic heading, true yaw relative to magnetic north, independent of time, independent of drift, independent of how many rotations the platform has completed. It does not integrate anything. It reads a physical field that exists whether your system has been running for 1 second or 1 hour. This is why the magnetometer is the sensor that grounds the entire orientation system. The gyroscope gives you fast, smooth, high-rate rotation data with no noise. The magnetometer gives you slow, absolute, drift-free heading reference. The correct approach, which has a name, sensor fusion, is to use both simultaneously, weighting the gyroscope for rapid dynamics and the magnetometer for long-term correction. This is what Madgwick filters, Mahoney filters, and extended Kalman filters do. Without the magnetometer input, all of them eventually drift. Now here is where the environment makes this harder than the datasheet implies. Magnetic interference exists everywhere. There are two categories, hard iron and soft iron. Hard iron distortion comes from permanent magnets near the sensor, motors, battery cells, ferrous hardware, speaker magnets in a phone. These create a constant offset vector added to every measurement. Soft iron distortion comes from magnetically permeable materials that distort the field shape without adding a fixed offset. Steel chassis, aluminum structures with iron content, certain PCB traces. These are field shape distortions that change depending on orientation. In a drone, both types are present. The motors alone generate significant hard iron distortion. If you mount a magnetometer on a drone and read it without calibration, the heading data is wrong by a margin that will make autonomous flight impossible. Not inaccurate, wrong. Calibration corrects for this. Hard iron calibration involves rotating the sensor through all orientations, collecting the output sphere of measurements, finding its center offset from the origin, and subtracting that offset from every subsequent reading. Soft iron calibration corrects the distorted sphere into a true sphere using a scaling matrix. Both steps are necessary for heading accuracy in real environments. Here is the part that most builders miss. Calibration is only valid if the sensor's relationship to the interference sources is fixed. If you calibrate the magnetometer on the bench and then reposition it relative to the motors, the calibration is invalid. If you add a new battery in a different position, the calibration is invalid. The calibration is not a property of the sensor. It is a property of the sensor and its environment together. This is why placing the accelerometer, gyroscope, and magnetometer on a single integrated module matters more than it sounds. When the three sensors share a rigid substrate, their relative geometry is fixed by the PCB. The calibration you perform for the magnetometer remains valid as long as the module position is fixed. You are not managing 3 separate mounting points, 3 separate coordinate frames, or 3 separate thermal expansion coefficients. The alignment between gyroscope axis and magnetometer axis is defined in copper, not in software assumptions. For sensor fusion to work correctly, all three sensors must share the same physical reference frame. A module enforces that. Separate breakout boards assembled on a frame do not, at least not without careful mechanical alignment and measurement that almost nobody does. The Texas Instruments TMAG 5273 used in the Multinav Pro Plus Sensors module is a 3-axis Hall effect magnetometer with a resolution that supports heading accuracy suitable for professional drone navigation and robotics applications. It communicates over I2C with a dedicated address. That is what is actually happening inside the orientation stack. The drift, the interference, and why the module geometry is not a convenience, it is a requirement. Now let me show you the hardware. 7 sensors, 1 board. The Multinav Pro Plus Sensors module covers the complete orientation and environmental picture simultaneously. Accelerometer, gyroscope, magnetometer for motion plus temperature, pressure, humidity, and air quality for the environment around it. Nothing is missing from this stack. The motion side and the environmental side operate in parallel. The BMI 270 handles high-rate inertial data for demanding platforms. The environmental sensors deliver live atmospheric readings. When your drone needs to know both its heading and the air pressure at altitude, this module is already reading both without splitting across 2 separate boards. These are not generic components. The BMI 270 from Bosch SensorTech is used in professional inertial applications. The TMAG 5273 from Texas Instruments is a precision 3-axis Hall effect magnetometer. ST Microelectronics, MEMS Vision, and Renesas round out the stack. Every sensor was selected specifically, not sourced for cost. All 7 sensors share a single I2C line with individual addresses. No bus collisions, no arbitration complexity. One connection to your microcontroller handles the entire sensor stack. For a drone or robotics platform with limited GPIO, this is not a convenience. It is a meaningful reduction in wiring failure points. 24mm by 18mm, that is the entire module. A platform where space determines what you can include, a drone frame, a wearable, a compact IoT node, can carry a complete 7-sensor orientation and environmental system in a footprint smaller than a postage stamp. The data this module produces is not static. Temperature, humidity, pressure, and air quality update in real time as conditions change around your deployment. For environmental monitoring applications or field robotics, you are not reading cached values. You are reading the actual state of the environment as it exists right now. Robotics, drone navigation, environmental monitoring, smart agriculture, industrial IoT, data network contribution. The applications are not limited by the hardware. The module is FCE certified and ships ready to integrate. Whatever you are building, the sensing layer is already solved. 270 inertial sensor without conflict. The result is one module, one I2C line, and a complete orientation reference system that has the correct physical geometry by default. The Multinav Pro Plus Sensors module integrates a Texas Instruments magnetometer alongside your motion sensors, so your platform always knows which direction it's pointed, not just how fast it got there. Most builders find out they needed a magnetometer after the first autonomous mission goes wrong. The physics was always there, the sensor just wasn't.